Let's take a look at this problem. It says classify each of these reactions as an exothermic or endothermic reaction and indicate the sign of delta H. So delta H is change in enthalpy, change in energy is probably an easier way to think of it. Exothermic reactions give off energy, so they give off heat, etc. For instance, when dynamite explodes, well, that explosion, I mean, that's energy being released with that gasoline burning. That's another example of exothermic. Exothermic reactions give off energy, and this energy can be used to do work. So when you burn gasoline in your car, that energy being given off runs your vehicle, basically. Endothermic reactions are the opposite. These things absorb energy. So for instance, if I put a piece of ice, it melts. The reason the ice is melting, it's absorbing energy from the atmosphere, the surroundings around it, and it causes it to melt. And then for each process, we got to give the sign. Exothermic reactions, you give it a negative sign. Endothermic reactions, we're going to give it a positive sign. Couple things, whenever I do this, I go ahead and I write out the three physical states of matter, and then there's transitions in between. So I say, okay, if I go from a solid, liquid, to gas, that's an endothermic reaction. It's got to absorb some type of energy to make that transition. So basically, if I go from left to right, so solid, liquid to gas, endothermic reaction. If I do the opposite, if I go from a gas, liquid to solid, so I'm going basically from right, so right means gas, up to the left, which is the solid, I have to give off energy to do that. So when you cool stuff down, you got to give away energy to do that. Like for instance now, if I put ice, water inside the freezer, what happens is the reason that water turns to ice is that it has to give off energy. So it gives off energy and then it forms a solid. This is why the back of your freezer or refrigerator, you can feel it giving off a little bit of heat. So that's that heat given off now from that water, etc. So let's take a look at this right here. First one is, it says butane burning in a lighter. Well, that's got to be an exothermic reaction. So fuels, they give off energy. That's going to be an exothermic reaction. We give it a negative sign. So delta H will have a negative sign for this. Next one, the reaction that results in a cold pack getting cold. So these cold packs, the reason they're getting cold, they're absorbing energy, normally from like water or something like that. So whenever something gets cold, that's endothermic. So again, it's the opposite of exothermic. So exothermic, it gets hot. Endothermic, you feel it getting cold. So again, it's going to be delta H, and we're going to give it a positive value. So endothermic has a positive value. Look at the next one, melting a gold ring. So when I'm melting, I'm going from a solid to a liquid. And so whenever you're going from left to right or solid to liquid, that's endothermic. That gold ring has to pick up energy in order for it to melt. And so that's going to give a positive sign. Next one is sweat evaporating from the skin. The way sweat cools you off. So sweat is a liquid, so you sweat it on your body, and then that liquid evaporates. So you're going from a liquid to a gas state. And when it evaporates, the reason it evaporates, it takes energy away from your skin. And that's why your skin feels cool. If you have a fan, that just increases the rate of evaporation. So evaporation, boiling, I'm going from a liquid now to a gas. That's an endothermic reaction. So you have to absorb energy in order to do that. Again, it takes that energy away from your skin. Next one is water condensing on a windshield. So in this case, you're going from water vapor, which is a gas, to liquid form. In that case, you're going from a gas to a liquid. You're going from right to left. You can think of it that way. So it's an exothermic reaction. It has to give off energy to go from a vapor state to a liquid state. And then last one, alcohol freezing. I mentioned this with water. So to freeze something, you're going from a liquid form to a solid form. So it has to give off energy in order to freeze. So in this case, it's exothermic and a negative sign. Next one here, It says the equation for the metabolism of sucrose. So sucrose is just regular table sugar. And so when you ingest sugars, carbohydrates, your body metabolizes it in order to produce energy. So you give off energy. It's exothermic reaction, essentially. In this case, we're saying how much heat in kilojoules is produced by the metabolism of, this is a 55 grams of sucrose. So you consume 55 grams of table sugar. Well, how much energy does your body get from that, basically? So we have the equation. We have sucrose plus 12 moles of oxygen forms 12 moles of carbon dioxide gas, 11 moles of water, and then gives off 5,644 kilojoules of energy. Couple things. We're going to use these mole-to-mole ratios right here. So this means 1 mole of sucrose, 12 moles of oxygen, 12 CO2, 11 moles of water, and it's going to give us the 5,644 kilojoules. So we're going to use these stoichiometric ratios for this problem. First thing we got to do now, we're going to rewrite the equation as 5,644 kilojoules as a product. So we're going to write that as a product. So exothermic reactions, you use that delta H as a product here. They give you grams of sucrose. Whenever you do the stoichiometry problems or stoichiometry, convert grams to moles. That should be automatic. And then once you do that now, we can convert moles of sucrose to kilojoules of energy produced. I rewrote that equation, and again, notice I wrote 5,644 kilojoules. I wrote that now as the product. And again, 1 mole of sucrose is going to give me that 5,644 kilojoules of energy. We have grams of sucrose when you're doing that. We're going to convert it now to moles. So we look up the molar mass of that. Again, always kind of cancel stuff out when you're doing that. So my grams cancel out. I got my moles of sucrose. And then the very last one is, well, 1 mole of sucrose produces 5,644 kilojoules of energy. And so at the end now, I get 906.37 or just 907 kilojoules. I wrote it as a negative sign to show you that that's an exothermic reaction. Next problem here, again, another stoichiometry problem. It says, how many moles of oxygen are produced by the decomposition of 3 moles of aluminum oxide? Take a look at this one. It says assume 85% yield. So we got to take that into account. So aluminum oxide, whenever you have aluminum, like aluminum cans, aluminum foil, it forms a thin layer. It reacts with the oxygen in the air. It forms a thin layer of aluminum oxide as a protective coating to that. So a few things about this one. We're going to look at the mole-to-mole ratios here. What's important is that 2 moles of aluminum oxide will produce 3 moles of oxygen. So you have that 4-to-3 mole-to-mole ratio. Write down what's given. So what's given now is our 3 moles of aluminum oxide. And we're trying to figure out, well, how many moles of oxygen will be produced by that? Well, we just look at the mole-to-mole ratio. 2 moles of aluminum oxide will give 3 moles of oxygen. So when I work that out, I'm going to end up with 4.5 moles of oxygen. So 3 moles of oxygen, of aluminum oxide, will produce 4.5 moles of oxygen. Now, you can't stop there because it says, okay, assume 85% yield, which means that I only get 85% of that 4.5 moles. So to finish that up now, well, I'm just going to multiply that 4.5 by 0.85, so I get rid of the percentage, divided by 100. And so I'm going to end up with 3.83 or 3.8 moles of oxygen. So I only get 85% of what I calculated theoretically from the problem. So pay attention to that. Pay attention to that 85% yield. Just don't stop at that 4.5. Pay attention to that 85% yield. Let's take a look at the next one here. This one is a little bit more detailed. It says how many grams of excess reagent. So whenever you do a chemical reaction, you make 1 limiting, 1 gets used up, and then 1 excess, which means it's left over. And the reason you do this, things in the lab don't work as nice and neat as they do with these equations. Again, all these calculations are theoretical. Your actual yield is always going to be lower than your theoretical. So we make one reagent excess to force the other one to get used up. So in this case, we have 4.36 grams of aluminum, 8.5 grams of hydrochloric acid, and we want to say, okay, which one of these is excess, and how much of that excess is going to be left over? The way I'm going to work this out, you got to work it out in 2 steps. He says, okay, let's determine how much hydrochloric acid is needed to react with the 4.36 grams of aluminum. And then we do the opposite. We say, okay, if I had 8.5 grams of hydrochloric acid and all of that reacts, we're saying, okay, how many grams of aluminum is going to be needed for that? And then at the end now, we got to determine the limiting reagent and then the excess reagent. So at the end, we're going to have to think a little bit before we decide how much is going to be left over. So I work it out. If I have 4.36 grams of aluminum, let's figure out how many grams of hydrochloric acid is needed to react with it. Again, for these stoichiometric problems, always go to moles. So I go to moles of aluminum. I go to mole ratio. So in this case, it's a 2:6 ratio. Moles of aluminum cancel out. And then I go to grams. One thing to notice is that whenever you convert moles to grams, you look at the molar mass, and it's always per 1 mole. So even though there's a 6 up here, never let that sway you. That's part of the chemical reaction. When I convert moles to grams, it's always grams per 1 mole. So in this case, it means that if all my 4.36 grams of aluminum react, I'm going to require 4.68 grams of hydrochloric acid. Let's do the second part. 8.5 grams of hydrochloric acid is what I actually added. I'm going to figure out, well, how many grams of aluminum is required to react with all that. So again, convert it to grams, from grams to moles, mole to mole ratio, 6 moles of hydrochloric acid, 2 moles of aluminum. Always kind of cancel stuff out. And then 1 mole of aluminum is 26.98 grams of aluminum. So in this case now, if all my hydrochloric acid reacts, I need 2.097 grams of aluminum. Looking at these 2 values, you have to decide which is the limiting reagent. Well, hydrochloric acid is going to be limiting. And the reason is, if all my aluminum reacts, I would need 17.68 grams of hydrochloric acid. We'll only have 8.5 grams. So it means that my hydrochloric acid is much less than what's needed to react with all the aluminum. So my hydrochloric acid, that's my limiting reagent. That gets all used up. It's only going to need 2.097 grams of aluminum. Well, I added 4.36 grams. So my aluminum is going to be in excess. And again, you have to think about that. Which is the excess, which is the limiting. And so the difference between the 4.36, the 2.097, that's going to be my excess aluminum for this particular reaction. Next one is when methane is burnt in oxygen. So this is a combustion reaction. For this problem, we actually don't have to write out the complete and balanced chemical reaction. It says the percent yield of carbon dioxide is 78.9%. That's my percent yield. If a theoretical yield is 28.9 grams, what is the actual yield of the carbon dioxide produced? So percent yield is actual divided by theoretical times 100. So again, your actual yield is always going to be less than your theoretical yield. Well, they gave us my theoretical yield. That's 28.9 grams. They gave us my percent yield, 78.9%. Well, how much did that student actually get when they ran this reaction? We do a little bit of algebra here. Actual yield is just going to be 78.9 divided by 100 times 28.9 grams. And we actually end up with 22.8 grams of carbon dioxide gas. So that's my actual yield. To test it, you divide a 22.8 grams, divide that by the 28.9 grams times 100. That's going to give you 78.9%. So in this case, they were just asking what this student got actually, and they give you the theoretical. So we didn't actually have to write the chemical reaction for this one. We can just plug it in into that percent yield equation. Let's take a look at this one. And this equation right here is to consider the following reactions. We have 2 moles of nitrogen, 5 moles of oxygen, plus 2 moles of water, and that's going to form 4 moles of nitric acid. And so this is actually a limiting reagent problem. We want to figure out which one of these gets used up. And again, with limiting reagent, the one that gets used up, that determines the yield of nitric acid I have in there. So we have the reaction mixture, contains 47.6 grams of nitrogen, 87.3 grams of oxygen, and 56.4 grams of water. What is the limiting reagent? And then from that, we can figure out how many grams of nitric acid is produced. And then the last problem is we're actually going to figure out the percent yield. When you're looking at these type of problems right here, there's no shortcuts with this. We're going to have to work out each one of these reactants because you can't tell by looking, just by looking at the masses, I can't tell which one's the limiting reagent. So we work it out. So we're going to do 3 separate steps. So we go work it out with the nitrogen first. So again, whenever they give you grams, convert it to moles. We're going to look at the mole-to-mole ratio. The mole-to-mole ratio is 2 moles of nitrogen will produce 4 moles of nitric acid. Convert nitric acid to grams. And again, whenever you convert to grams, remember, it's always per 1 mole. And so you're going to end up with 214.32 grams of nitric acid. So if all my nitrogen reacts, I'm going to produce 214.12 grams of nitric acid. But again, we're not sure if that's a limiting reagent or not. Let's go ahead and do the same thing for the oxygen. And again, convert the oxygen, the grams to moles. Look at the mole-to-mole ratio. Again, in this case, it's a 5-to-4 ratio. That last part is the same. 63.02 grams of nitric acid per 1 mole of nitric acid. And so now, if all my oxygen reacts, I'm going to produce 137.54 grams of nitric acid. That's theoretically there. And then finally, we do the same thing for water. In that case, the mole-to-mole ratio is a 4-to-2 ratio. And we're going to end up with 394.48 grams of the nitric acid. So what happens is the amount of nitric acid produced is always going to be the lowest amount. And the reason is I have enough oxygen just enough to produce 137.54 grams of nitric acid. After that, the oxygen is gone. So even though I have enough nitrogen and water to produce more, well, it can't react if there's no oxygen. So oxygen is a limiting reagent. That's the one that gets used up. The limiting reagent tells you how much product you're going to get theoretically. And one thing, again, just to emphasize, you can't tell by looking, because if you look at that, even though I had more grams of oxygen to begin with, that's actually the limiting reagent. So you have to just work it out. There's no shortcuts to these types of problems. Last one is, what is the percent yield? So again, it's actual over theoretical. So theoretical is what we get from calculations. That's going to be 137.54 grams. This student got 74.8 grams. That's what this student got actually in the lab. Multiplied by 100, and then you end up with 54.4%.